lots of time here, and this will connect to various other things that we've heard about and topics for questions and discussion. So I'm going to tell you about a recent paper, which is with Jivan Chandra and Viraj Marulia, but it touches on, so the point of this paper is to try to study what I think is probably the simplest example of an ensemble average duality in gravity more than two bulk dimensions. Okay, so it's going to connect to various other examples of ensemble average duality, but kind of bring it together into this example. So I want to start with a few pieces of background and to sort of set the stage. So first of all, in ADS3, there's at least a partial semi-classical and to all orders holographic duality between the bulk theory, both coupled to external point particles, and in situations like this where you have some higher topologies where you get hyperbolic three manifolds in the bulk, and you can do gravity to all orders around these hyperbolic three manifolds and match that to an ensemble average over CFT data in the bound. This of a wormhole like that is this 3-point wormhole. So all of the pictures that I'm going to be drawing are space-time pictures, Euclidean space-time picture. So this one is, so there's two copies of the dual CFT, and I'm using the matter in this case as three defects that are going through. And this wormhole calculates the 3-point function, average 3-point function in the dual CFT. So this function C0 is a known special function that can also be calculated by conformal bootstrap. It's sort of like a Cardy formula for OP coefficients that was found earlier by bootstrap methods by Scott and collaborators just using CFT. And this Cardy formula for OP coefficients is dual to the two boundary wormhole that you have in ADS3. That's the simplest example, but there are lots more elaborate wormholes that you can study. Another example is the one studied by Malleson and Maus. So in fact, in ADS3, you can get two boundary wormholes just by taking any hyperbolic two manifold and putting it together with an interval with the right warp factor. So you can turn hyperbolic two manifolds into two boundary hyperbolic three manifolds. That's why the simplest one here needed three defects, because you need three defects to get a hyperbolic metric on the two manifold. So you can either do three defects on a sphere, or you could do one defect on a torus, or you can do no defects at all if you go to two. So this one in the ensemble interpretation calculates for you the genus 2 partition function squared. I'm being a little schematic here because the genus 2 partition function depends on moduli, and we have to keep track of all that. But I won't go into that here. So you can go to more boundaries. Go to more boundaries. One way to construct these wormholes with multiple boundaries, any number of boundaries, is to add enough defects, so hyperbolic two manifolds on the slices through this geometry. So like in this case, be calculating for you a CFT 4-point function cubed average. So why do we get that? Well, we have three boundaries, so we have three copies of the CFT. On each boundary, we have four operators hitting the boundary. So these are the boundary conditions appropriate to a CFT 4-point function. This calculates some connect contribution to that 4-point function. If you cut it here, then that's a sphere with four punctures. You could put a hyperbolic metric on that sphere or full punctures. So these are on-shell solutions of three-dimensional gravity. These, yes. Yeah. So, well, the equals is actually equals, but I bar means. And in this case, what the bar means is you expand this in expand the three correlators in conformal blocks, and then you'll get a sum, you'll get a triple sum with things like C12P, C34P, C12Q, C34Q, etc. And then one defines the average of these OPE coefficients according to this ensemble. And if you want this to be exactly equals, then what you should do is you should take the Gaussian average using the variance defined by C0. So it's like if you take this Carty formula and treat it as an exact approximation, that's this contribution. Now, in principle, you should add higher contributions, which are non-Gaussian. Those will give corrections. But term by term, this one, to all orders, well, we didn't know this at the time when we did this work, but now using Virasoro TQFT, they can now calculate these wormholes exactly to all orders in perturbation theory around this given topology. And then this is an exact equal sign of orders perturbative. What I think the Virasoro TQFT calculation is exact at finite C for the contribution from a given topology. But I don't know the answer to that. The, yeah, so there are non-perturbative corrections to C0, and I guess you're saying those don't show up in this topology. Yeah. I don't know if it's known how to get the non-perturbative corrections to C0 from the bulk. Is that known? Do we know if that works though? I mean, there in some examples, not systematically, I think. Yeah, yeah. Uh, yeah. Why is it Gaussian? Whether the practical answer is you just try that because it seems like a good place to start, and it works. It gives the right answer. A slightly more technical answer to that is that I think it's because ADS3 has no local degrees of freedom, and so it's the fact that the geometries are locally. What that allows you to do is to construct geometries like this, but and when you glue together these pieces of the black hole, you get a relatively simple set of rules for constructing the ones, and that corresponds to the Gaussian approximation. It's important here that the Gaussian approximation is being taken on primaries. So these are a bunch of conformal blocks in here too, accounting for all the descendants. So the idea here is that the primary are like, those are black hole microstates and those are as random as possible. And then there's descendants, which are more like the low energy field theory. Those aren't random at all, so you don't average over those. And it's just nice that the bulk expansion in topology sort of organizes itself as around the Gaussian approximation. Yeah. It's more like Euclidean channels. It's like these Euclidean windings of different OPE channels. Yeah. Oh, yeah. Yeah. Yeah, I see. Yeah. Ah, absolutely. Yes. So and the reason that so before bar, this was manifestly crossing invariant. I defined bar. I said we define that bar by expanding in a channel and then doing the average. And so if you put the bar, this is no longer crossing invariant. And to make it crossing invariant, you now have to sum over the different ways of doing the expansion. Those will correspond to different topologies that you should consider the bar. So that is the basic story. So in that case, it is rerouting. I was counting those as different topologies in the sense of matter winding around. Yes, grading. For that one, it will be different topologies. Yeah. Good. So now story in higher dimensions. In higher dimensions, it would be very hard to do something at this level of detail, but conceptually, I think that different. And in higher dimensions, can get quite far if you assume spherical symmetry. And in fact, the wormholes that you can construct are very similar, but we have to interpret the pictures a little bit different. Okay, so how did we get wormholes in ADS3? We inserted enough matter in order for the boundaries to separate. The way I like to think about this is that if you in the middle and imagine evolving in Euclidean time, the boundaries would like to join to each other. Curvature or matter going across, you can make the boundaries bend outward so that they never join and you end up with disconnected topology. You could do the same thing in higher dimensions. It's just that for local operator insertions, it's to solve the Einstein equation. Now there are local degrees of freedom. But what you can do instead is you can use spherically symmetric matter distributions, and then you get not all, but many of the same wormholes that you can get in lower dimensions. So now these are pictures in higher dimensions. Again, these are Euclidean wormholes, but you have to interpret them a little bit differently. So every point on here is one. I'm using little, this is in the ADS little d plus one. So every point on here is a transverse sphere. And therefore these matter distributions, these matter things that are going across are not point-like defects like they were in ADS3. These are now sphere shells. You don't have to use shells, but the nice thing about using shells is that they're localized in the other directions on this picture. And so that's a type of matter to work with. This is Jeevan and I did a couple years ago in attempting to lift some of these results of ADS3 into and see what we could do in higher dimensions. The story of the ensemble average there is also similar. The blackboard is, what's the goal? In this case, it's a two boundary wormhole. Think of this as like you put in time direction, and this is some radial direction, and then it's spherically symmetric. There's really maybe this will help if there's edges here. I'm not drawing them because they're not actual boundaries. This is just capping off of, maybe it's easy to think if I draw it this way, but now it's a little impressionistic. Each boundary is a sphere, each boundary is an SD. So if I draw it this way, then each boundary is one of those spheres, and there's a shell that looks like this going, and there's a shell that looks like this going across the bottom. Which a cross section, in this case, let's say each cross. Does that make sense now? That's right. That's right. Well, the junction condition, yeah, that's right. The junction condition, these are solutions using the junction condition, but if you have a massive particle, then you can get solutions that are just like this by treating the shell as a bunch of point-like particles traveling next to each other. Good. What about it? Yes. These are all in any dimensions. These work in any dimension. Well, sorry, I've used two different D's here, but let's use little d. Okay, little d is the boundary dimension. It can be any. We could do a CFT4, and the bulk is ADS5. No, sorry, this was so each point here is an SD minus 1, and the whole thing is an ADS D plus 1. Yeah. Right, yeah. Okay, these pictures clear? So the story of ensemble averaging there is similar. In fact, it's easier, not because it's actually easier, but because of spherical symmetry. Because we've imposed spherical symmetry, we can ignore descendants. Now, in higher dimensions, the notion of descendant is a different one. It means, in CFT2, it means Virasoro descendant. In higher dimensions, it means any dressing with gravitons. But that dressing with gravitons is subleading in spherically symmetric states. So at leading order, you just ignore all the gravitons. This is, as a gravity fact, this is a familiar statement of the Birkhoff theorem that when things are spherically symmetric, they have to just be the Schwarzschild black hole locally. In fact, like higher dimension gravity spherical symmetry is of similar complexity or even easier than studying ADS3 because everything is locally Schwarzschild when things are spherically symmetric. Just like in ADS3, everything is locally vacuum. Yeah. There's matter hitting the boundary, so that violates the boundary conditions of width. Correct, because there's sources. This would be dual. This one would be dual to a 2 of these operators squared. So there's a non-normalizable insertion at the boundary. Yes. As far as I know, that's the only reason. And I think you could probably construct them with local optics. Yeah. Uh-huh. Yeah, these are just Euclidean version of that. Yeah. If we think about single boundary version of this, so not the wormhole, but just a single boundary with a shell, then this is the Euclidean version of the Vadia, or sort of a Vadia type collapse, where you have well, I'll say more about this one later, but this is a with the Schwarz hole glued to human, you could go to Lorentzian and get a Vadia out of it. So to write out the well, first of all, since these are spherical shells, they're created by spherical operators. I'm going to call these spherical operators d sigma, which is a non-local operator in the dual CFT. So the states that we're discussing are created by acting with this spherical operator. If we take that spherical operator and we expand it in energy eigenstates, it's got some expansion, and the duality, the ensemble average duality in this case is the path integral on the wormhole at the semi-classical level. So really, I mean e to the minus the gravity action, probably plus one with corrections, but we haven't calculated those. The e to the minus gravity action is the average of a bunch of these. So you have just two, if you calculate the norm, psi, then that corresponds to the black hole. That would be the single boundary case. And in order to define the ensemble, if you have many boundaries, then you just take many copies of psi and calculate the ensemble average, where now this ensemble average is defined expanding in these eigenstate coefficients, and AM AN bar is delta MN times some smooth function of energy. So again, it's very similar. You just expand your state in some coefficients, and then do a Gaussian average on the expansion coefficients. And all of the wormholes, all of the K-boundary wormholes that you can construct from all the including these thin shells match their on-shell action matches this Gaussian average. This is similar to what happens in the West Coast model in two-dimensional gravity, really a higher dimensional version of the West Coast model. Since it's using spherical symmetry, it's a similar level of complication. The only real difference, which is a big one from the two-dimensional case, is that you can't do these calculations exactly and understand the full sum over topologies. You could just understand the leading semi-class so far. Good. No. So this is the analog of C0 squared in higher dimensions, and it's not derivable from bootstrap. That's like if you could derive that, then you could also derive the free energy of the ADS for ADS5 black hole, which is not doable from CFT. So in general, the answer is no. You have to, the way this works is you view this as input from the single boundary solution. So you take gravity input from the single boundary solution, you use that to define the variance of the ensemble, and then you compare it to the multi-boundary solutions and you check that it's consistent with that. So you get input. So the story here is you get input from the bulk and then you compare it to the higher topology. Yeah, that's right. If you view C0 as not as coming from the bootstrap, but as coming from Right. That's right. That's right. I think that's right. I think that's right. Now, in that case, it's less universal. So in gravity language, it will depend on higher curvature corrections in the bowl. So there's really kind of an infinite amount of input that you need there. You need the Einstein block. Somehow it needs to reorganize, and you need the whole Einstein block instead of the Virasoro. Correct. Yeah, it will. This C0 knows about it. Sort of in higher dimensions. What do you want to average? You want to average black hole microstates. You don't want to average gravitons. And so first you have to take off all the gravitons. We don't know how to do that. Yeah. Yeah, there would be six. Uh-huh. Yeah, this is the cyclic contraction. It's the one that you would get from the picture. So this is the cyclic contraction of the six A's in the expansion. That's right. This is a good question. But when it comes to thin shell, we don't know how to think about the non-Gaussianities. In principle, there could be so the analog of what you might try in higher dimensions is you might try some shell. You might try to look at some wormholes that look like this, let's say. But now these shells are hitting each other. They can't go around each other like point particles can. So now you have to worry about the interactions of the shells. And my guess would be that this is reflecting some additional non-universality in the non-Gaussian contributions to the ensemble are probably less universal in higher dimensions and could depend on the details of how you things like this. It could be very different for different types of shells that are made of different things. In classical string theory, um, yeah, I think I think that's right. I think to get the Gaussian approximation, I think it's important that things are locally trivial, sort of. Like in this case, locally Schwarzschild, just moving a bunch of Schwarzschild, that corresponds to the Gaussian approximation. I don't think that string theory will like even if we just had some light fields, forget string theory, if we just had a massless scalar field, then I don't think there would be anything as simple as a Gaussian approximation, because now this matter wouldn't be localized here. It would be sort of spreading out everywhere throughout the wormhole. And then I don't think there would be a Gaussian approximation. Maybe there's some way of treating that as Gaussian, but at least this won't quite work. Okay. So this is really the background for what we did in this recent paper, which is to study which is basically to put these two together and to study thin shells in ADS3. Okay. So the new work that I want to tell you about now is what I think is the simplest ensemble average duality, at least the simplest that we know of. It's spherically symmetric ADS3 holography. Okay. So thin shells in ADS3. It's a nice example to look at because it's doable completely analytically with simple formulas. You can write down all the geometries. You can solve for these, you can solve for the ensemble by bootstrap, some connections to Liouville that I will tell you about. So where I'm here is what's written on this board over here. So the idea is to relate these thin shell black holes and wormholes in ADS3 to the statistics of line defects in CFT2. So we need to start with some study of line defects in CFT2, especially in the holographic limit. And the way that we're going to show that these two things are equal is to show that they both reduce to a third problem, which is line defects in Liouville CFT, which I will call L sigma. And the idea is going to be to show that if we study the statistics, so if we study the black holes, that will give us an effective Liouville theory corresponding to line defects in Liouville at the same value of the center. And also, if we try to study the bootstrap of these line defects in the dual CFT, that will also reduce to the same problem in Liouville CFT. And one can phrase the point particle duality in a similar way. But here, these are easier to study because of the spherical symmetry. Okay, so it's important to keep in mind that there are two different line defects that we're talking about here. There's the one that we're really interested in, D sigma. That's the one in the dual CFT that has statistics we're going to study, et cetera. And then there's this other line defect in an auxiliary Liouville theory. This doesn't have any statistics. This is just one theory, Liouville. And we don't even, deep down, we don't even care about Liouville. We're just using it as a trick, as an auxiliary theory that we can use to do calculus in the theories that we care about. So I'm going to start with the Liouville side of things. Yeah. I suppose there probably is a calculation along the expanding in some other channel. There are infinitely many channels because we're talking about these defects, because we're talking about extended operators. So there are infinitely many channels. I'm not really sure how to, yeah, right. So Liouville is the 2D CFT with the following action. The state psi is from cutting the boundary solution. So the state psi lives, you take the single boundary black hole solution, then that one is psi. Now, if you cut these wormholes, that's not psi, that's some more complicated state. I may mention that again. So in Liouville theory, we usually study the local vertex operators, either to alpha phi. But since we're interested in things with spherical symmetry, we're going to study this non-local operator L sigma, which is defined as E to the M over 4 pi of the Liouville field phi. So this is an integral over a dimension 1 surface called sigma, and this is a line. For comparison, people have studied in the ON model. People have studied you take phi of one of the phi fields of the ON model. You integrate it along a line with a similar formula. Then that's been used as a model of impurities in various condensed matter and StatMech contexts. But this is a situation in Liouville CFT. This operator is not conformal. This is not a conformal effect. It has mass parameter m, and the information of the Liouville field is such that this is non-trivial under conformal transformation. The goal of the next couple minutes is of this line defect in the semi-classical limit of large C. So why is that the goal? Well, we're going to come back and reduce these other problems to that calculation, but for now we're just studying this line defect in Liouville because we want. No, I don't think so. That's a topological. That's, I think, topological, and this is not topological nor conformal. I don't think it's. Yeah. So some of these results are going to apply at any value of C, but these matrix I'm going to calculate at large C. The reason, technical one, that we can calculate them using semi-classical methods. So we're going to look for classical solutions of the Liouville theory with the insertion of these line defects, which just means that we want to add this term to the action, one for each line defect insertion, and then solve that modified Liouville equation. Classical equations of motion are dd bar phi is a half e to the phi. That's your standard Liouville equation, which describes hyperbolic two manifolds, together with a junction condition at each defect, which you can write like this. So when you insert the line defect and vary the action, derive the equation for motion, it tells you that there's a jump in the normal derivative of the Liouville field that's controlled by this mass parameter m of the defect. So that means that to study these defects, what we need to do is we need to study hyperbolic two manifolds glued across interfaces with this gluing condition. The simplest one we can look at is a single line defect. Which would correspond to one function of this line defect operator L sigma on the trivial topology. You can kind of just think of hyperbolic manifolds look and figure out what this one's going to look like. Contortions and draw a picture. So the solution, the hyperbolic solution here, is going to have a line defect and then two hyperbolic disks on either side of the line defect. And there's a curry type thing at the defect. Okay, smooth manifold. This is as embedded, smooth manifold as embedded in the three-dimensional space I'm drawing it in. It's hyperbolic at top and bottom with metric equals 1 over sinh squared of a plus minus a constant. Y is this direction. I don't know if I said this. Maybe this wasn't clear. So the Liouville metric e to the phi, the Liouville metric e to the phi dz squared is the hyperbolic manifold. So instead of thinking about solutions of the Liouville equation, we can just think about manifolds, and that's what I'm drawing. And so each of these caps here is a hyperbolic disk, and then they're being glued at this interface. The line defect creates sort of a folded part of your hyperbolic tube. This is called the G function of the defect, because it monotonicity properties under RT flow. But I'm not going to go into the RG flow, but focus on other things. So the next one we can look at would be a 2-point function, like LL, still on the trivial topology. And again, you can solve the Liouville equation by thinking about gluing together hyperbolic two-manifold. So if you look at this one for a minute, how do you make a hyperbolic two-manifold with two line defects? The answer is that, well, first let's draw our two defects. Okay, so hyperbolic two-manifold with a topology of a sphere. Well, I fill in a hyperboloid here, and then put hyperbolic disks on the end caps. And so that's the solution corresponding to the defect function. You can write down the Liouville solution on the explicitly, and for each of these others that you can look at, and for each of these solutions, you can then calculate the correlation function semi-classically by taking your Liouville solution and plugging them in to the Liouville action and calculating the on-shell action. Let's go up here. That's right, but if you insert enough operators, then you can often get a semi-classical solution. In this case, you need to take the math parameter bigger than 1 or 2, depending on the details. For the single one, you need to take m greater than 2 to get an on-shell solution. Yeah, this has just a distance. Well, you can also tilt them, but for our purposes, we're just going to make them parallel. So then there's one real modulus, which is the distance between. No, that we don't integrate over that. We calculate this at tau minus tau, and that corresponds to this distance, and then the 2-point function is a function of tau. So correlators, you calculate them as an on-shell action in the semi-classical approximation. So you plug it into the action and extract that the correlation functions. I said a few minutes ago that our goal, I said up there that our goal was to calculate the matrix elements. But once you have enough 2-point functions, you can figure out the matrix elements. In this case, what you need to do is you need to, so like from this one, we can learn 0 L sigma P by doing a spectral decomposition on this 2-point function. If we do the same thing at finite temperature, which you can do, you just have to do similar things on a torus, then you can learn P prime, L sigma P. And so by finding these classical solutions, do spectral decomposition on the resulting correlators, you learn the matrix in the semi-classical limit. So I'm going to write this as e to the c over 6. H prime, where those are the conformal weights of the two states, P and P prime. And I'm not going to write it down because it's got some arctotans and logs and stuff like that. But this is a very simple function. This CL is a simple and easy function to work with that just depends on conformal weights, and it's got some logs, and depends on H prime and the math factor M of the defect. should have you should think about this as being the sort of defect analog of the DOZZ 3-point function in the semi-classical limit. M is dimensional, yes. M. Well, there's important M dependence. What? Wait. It sort of enters similar to the scaling dimensions. It's like the fact that those really tau is not just a power law in tau, the whole stated function of tau, and so this is some function of yeah. Yeah. Yeah, I've set the Liouville cosmological constant to 1. So that's right. Yeah, M is positive. M is positive. In fact, for these on-shell solutions, M is bigger than 1 or 2. Yeah. If it hits itself, so I yeah. If you just want to make it curvy, then I think that's that's conceptually the same. It's just going to be more complicated. You know, the nice thing about making it straight is that you don't need to worry about descendants. And so when you do this spectral decomposition, it's very easy to expand in primary. I think if you start making it curvy, then you'll have to worry about descendants. If you wanted to also have some interesting topology or intersections or anything, then I wouldn't know how to do that. But just making it curvy is not too good. Yeah, you can do that too, and that will calculate. In fact, that's another way to extract these matrix elements. That will directly calculate for you the matrix elements where these are light. Whereas, so that would be like the case where these are below C over 24, because they're conical, you're thinking of conical defect. Whereas this describes the spectral decomposition of the torus 2-point function gives you the. That's true. That's true. I don't think we did that calculation, but that should also work. And the heavy ones are related to the light ones by an analytic continuation, although it's a little subtle, but if you do it carefully, they are. Yeah. Um, let's see. I don't. That's the case. No. Um, um, yeah, I don't think that'll be the case. I think that the junction will. Yeah, yeah. Okay, so that's all we needed to do in Liouville. And now we want to look at each of these other problems on the big board and reduce them to the Liouville problem that we just solved. So we'll look next at the CFT. I'm calling it, well, I'm calling it the compact CFT just to distinguish it from Liouville, non-compact. Okay, usually we just call that the CFT. This is going to be the dual CFT in the large C limit. This is a compact CFT, and a lot of what I'll say is true for any. A lot of what I'll say about this is true for any C greater than 1. A line defect d sigma that transforms under conformal transformations like the Liouville defect L sigma. Okay, so for example, and this will be the example we have in mind for thin shell black holes, you can take of primary operators running along a line, and the limit of a large number of these local operator insertions. This is something you can do at large C, because you could take the limit of a large number of operator insertions while simultaneous with the large C limit, and you can do this in a way that holds fixed the energy of the state created by this operator. Okay, so the kinds of line defects we have in mind are like these continuous products of local operators. Why is that the same as the Liouville one? Well, remember what the Liouville line defect was. It was an e to the integral, but you can think of that as a limit of a product of Liouville vertex operators. So these type of defects that we're talking about are like products of primaries. It's the definition of the operator is the same limit that studied in paper with Julian Sonner and Karaganos and Penton and Ravai. The kinematics of where we're going to insert them is different, because there we were just doing the null collapsing. Kinematics were much easier to deal with. And here we want to be more general and get the one. We're also going to assume that of these defects that they confuse the identity in a way that I'll make it in a second. And then the claim, which will be from other situations like the Carty formula or the C0 formula for local operators, is that there's a universal Carty-like behavior of these operators. There's a universal matrix elements at high energy or high conformal weights that is the matrix I d sigma j squared and averaged over states, right? That bar states. So this is not some like holographic ensemble averaging type average. This is just a microcanonical average like you have in the Carty formula. That this average matrix elements is methodically a universal function that I'll call C0D, which depends only on the weights HI and HJ and the mass parameter of the defect. And there's a bar. Sorry? Yeah. Oh, yes, yes. M is fixed. Yeah. You have to assume that it exists. You can always make it in a large C theory that has some point like dusty operators. But we're just assuming that we have a CFT that has these two, that has a line defect that transforms this way that computes the identity. Correct. And this statement is true at finite C. It just requires Virasoro algebra, but we don't know if there are holographic theories that have defects like this, since the only example we have in mind is the holographic one with the infinite number of times. I don't that non-holographic theories or Oh, I don't see that would exist. I don't see why that would exist. I would expect, well, there may be situations like in gauge theory where you can cook up situations like if you had a Wilson line that created this operator, maybe there are situations like that. I don't know of any in detail, but it should be made of something. It could be made of something that's charged, and then it would only exist as a non-local operator. That's right. This example, that's right. The example of making it from primaries requires also taking large C, so that then you don't have to take the weights to zero. You can just take them much less than C while holding them finite. But yeah, if you wanted to, you wouldn't want to use this example of finite C because then you'd have to take the weights to zero. I think you could have situations where the particles interact. Um, oh, I see. I see. Yeah, that's true. Yeah, maybe you could get it to cancel. Yeah. Yeah, I think if they interact, that's beyond the identity approximation probably. So I don't know if you could use that. Not derive this formula. We're going to use a trick that actually also works for local operators and makes the derivation pretty easy, which is to use ZZ brain technology. So the idea is the following. We start with a 2-point function of the defect in the compact theory. That's the picture that I just drew. So we have some 2-point function of the defect. What we want to take, we want to study the limit where they come close together. And then we're going to project onto the identity around circles like this. Okay, so that's an assumption that there's an identity block that runs in that channel. And if there's an identity running in the channel, that will dominate the correlator as these operators come very close together, and therefore, when we do the spectral decomposition along here, the identity block will determine the asymptotics of those matrix elements. To actually do the calculation, there's a nice way to do it is using ZZ. So the identity block in the compact CFT is equal to a Liouville calculation where you cut this picture in half, you put a ZZ boundary condition on the real line, and then you insert, I don't know if my color coding has been consistent here, but then you insert the L sigma operator in this Liouville calculation. Okay, so this is a calculation in Liouville on the upper half plane. This is a calculation in a compact CFT on the full plane. But it's generally true that Liouville calculations with ZZ boundary conditions calculate for you identity conformal lines. The reason for that is that the ZZ boundary is a special conformal boundary state where the only operator on the boundary is the identity. Okay. So instead of, so there are various situations in holography where you want to talk about identity conformal blocks. All of those can be rephrased in a nice, convenient way using these ZZ boundary conditions. But it's equivalent to other methods that have been used, like the monodromy method of Zamolodchikov to calculate these large C blocks. And – I mean, let me write this as a formula because it's kind of a cartoon right now. There's the formula is that the identity block in the compact CFT. Well, this is just a Virasoro thing, but we could compact CFT. This identity block is equal up to a known normal oh sigma ZZ. This L sigma has parameter tau, which becomes the modulus of the controller block. It's literally equal to this little correlator on the upper half plane with a ZZ condition. This formula just has one Liouville. Right. Yeah, the block has only one parameter, right? Because they're all scalar. So this formula is literally true for the chiral block. This is the chiral block. So the chiral block corresponds to one copy of Liouville. In the compact CFT, yeah, if you want a correlator, you get mod squared of this. And what this means for the compact CFT is that now we can take our result from Liouville, immediately read off the universal formula for defect matrix elements. And it looks like this. C of H prime M equal to the Liouville matrix element that times some extra junk that comes from the ZZ brains and just ends up amounting to pretty factors. So the universal formula for the asymptotic matrix elements is Liouville times some party factors. I've dropped some phases here. I'm oversimplifying a little bit for the case of like light operators. You have to worry about these reflection phases. But this is the way, this is about right. Yeah. Yeah, that's right. That's well, the fusion kernel is a property of the compact CFT, so there's no boundary there. But you can think of this as some identity block, and that what we've done is calculate the fusion kernel for this identity block. That's another way of saying it, and it's equivalent to this form. Yeah, that's right. Yeah, yeah. You could do the same thing for the more famous C0 formula of Scott and collaborators, and you can rederive. So they also found a relationship that, remember, this is kind of like VOZZ. This is some Carty factors. Similar story holds there, where you get a relation between the universal C0 of compact CFTs and the Liouville auxiliary. Yes. Well, it's actually a vertex op. You replace it by a vertex operator, and that becomes your third thing in the OP coefficient. Yeah, Yeah, you can think of it that way. When you do a calculation this way, the way it arises is the wave function of easy state is like P ZZ is like square root of rho zero. I can't remember if it's one of that or one of that. So that's how it comes out. And again, the nice thing about this formula is that it's just a log. I didn't write the explicit formula, but there's just a nice formula for it. So now I'm going to go to uh, which is the comparison to gravity. And so here we're talking about 3D. Well, I shouldn't call it pure. It's 3D gravity plus shell incorporated by the junction conditions. Dust shells you can think of as code one collections of particles moving on GDZs. So you have a bunch of these dust particles and you add them to the action, adding these M particle integral dl over the whole line of these dust particles. By adding up all these geodesics, you can put them together and make these shells. And the dust shell is dual to the d sigma operator, the line defect of our holographically dual CFT. Simply because we're going to choose our dust shell to be codimension 1 and spherically symmetric. So that's the same. The source for those are these d sigma operators. Yeah, if it's pressureless, well, yeah, for pressureless dust, this kind of follows from the standard dictionary because pressureless dust is a bunch of that's the same as a bunch of particles, and the individual particles will act like primaries. So yeah. So the graph side is the this type of matter uh, contributions is dual to a approximately Gaussian ensemble. Now is an well, in general, we think of these ensembles as ensembles of CFT data. Well, as we've discussed in other talks and discussions, maybe there's some deeper ensemble of all CFTs or ensemble of microscopic theories. But for our purposes, it's an ensemble of CFT data. And in this case, data means the matrix elements of the defect operator. Okay, so these are the random numbers, and the ensemble is defined giving which in order to match our bootstrap calculation, the variance is this step function C0D that we just extracted from the identity block. Since Gaussian, it's enough to tell you the variance, to give you the leading contributions to all of the higher moments, and this will give us all of the wormholes that you can construct in the bulk, so long as the shells don't intersect with each other, right? Like we talked about before. the shells start intersecting, then things get more complicated. Start with the black hole itself. Is a solution with a single boundary and a shell. So this will correspond to the CFT calculation of the 2-point function d sigma. So here here's the first insertion that creates the state in time tau. Then there's a second insertion up there. The Euclidean solution is found by solving the Israel junction conditions. It will be vacuum ADS3 outside the shell. And inside, it will be a BTZ black hole of energy and angular momentum J. Now, I need to say a few more words in order to explain this angular momentum point of view. Okay, so if we just insert the shell, then you would think the angular momentum would just be 0. But what you can do is you can give the particles in the shell a flavor, give particles a different flavor, so they can only contract with each other. And then if I think of this as particle 1, 2, 3, 4, 5, etc., then up here, when I insert the second defect, I can do a shift in how the dust particles are labeled. So now, if you insert this second one with a shift, the particles need to do this in order to conserve the charge in the bulk. So you have these two copies of the shell, but by shifting the upper one, you can create states with angular momentum. Yeah, so in Liouville, there was no flavor. In Liouville, these line defects were perfectly translation. But when you go to the compact CFP, you can just declare that the identity only, so if we want to phrase this in terms of continuum, then the statement is that it's now on shapes like this that you assume the existence of an identity projection. If you construct it from dust particles, one way to do that would be to give them a flavor, but you could just declare that this is where the identity shows up. So in the compact CFT, the defects are not translation invariant. The mass you could make, you could also do this with the mass by changing the mass. But in our case, we're not going to do that because that would be, I don't see a problem in principle, but that would be complicated. Here, we're just going to add one parameter, which is the shift, the relative shift of the two defects. Yeah, that sounds hard. It sounds hard. Yeah. No, I think you need no, I think you need a million flavors, or however many particles there are in your shell, if you want to make sure that this one will land way over there, because you don't want it to be able to land at any of these points that would be lower action. You need to force it to go all the way over there. But then particle, what's this part? Where's this particle going to land? We might go up there. We don't want that. Yeah. Yeah, but I guess the question is how what matter content would you actually put in the theory in order for it to end up having a marked point? And one way to do that is to give them a flavor. the metric on this black hole is very easy to write in the case of field momentum. Just d rho squared plus cosh squared rho e to the phi dz squared. With it gets much more complicated with angular momentum, but with zero angular momentum, this is the metric. So let's describe why this works. Well, this is a slicing of the geometry where you slice it like this. At any fixed value of rho, you just have to solve the Liouville equation. And in rho, the only thing you have to do is put in this cosh squared rho factor. You can see immediately that this is a solution of 3D gravity because hyperbolic 2 in this warped metric, turning it into a hyperbolic 3 metric. It's the same sort of metric we use for 2 boundary wormholes. But in this case, the Liouville solution, phi, is the Liouville solution that we talked about previously, which is the Liouville solution on the upper half plane, corresponding to the line defect with for half plane with the ZZ boundary condition. Okay. So let me say it again. So we have these Liouville solutions on the upper half plane. L sig Z. This is just one defect on the upper half plane. We used those to calculate the universal asymptotics of the OP coefficient earlier. And now we're saying with that same Liouville solution, we can the bulk geometry corresponding to these black holes. So that's sort of the basic connection that's going to make all the formulas work out in the end, is that actually both calculations, the calculations of the OP coefficients reduced to this Liouville with a ZZ brane, and the calculation of the black hole also reduce the Liouville with the ZZ brane. So you're going to get the same answers in both and bound. So for the black hole, the formula is e to the minus s grav equal to some normalization constant on e to the minus 2 s Liouville, which is a calculation on the upper half plane with a ZZ boundary condition. Which is also the defect 2-point function in the dual CFT. A lot of different moving parts here. Maybe did that make sense? Question. This is the three parts. So the gravitational action is the Liouville with ZZ boundary conditions, and that's the same as the defect 2-point function, the dual CFT. In this case, the block approximation, because that's what we did, is we matched the identity block to the defect 2-point function. Okay. So this formula is still true at finite C. This formula is exact. That's the only statement. Well, we can't calculate either one of them, but they're equal. The thing that we can actually calculate explicitly and find a nice formula is the large C limit. Yeah, in fact, the thermal field double state is essentially 2 copies of ZZ. Not the thermal field double, but the thing that you would do in Liouville to get the thermal field double in is essentially 2 copies of ZZ. Yeah. So in a paper a while ago now with Julian and Tarek and Anton, studied the Vadia collapse using some CFT stuff. That corresponds to the OPE limit where these come all the way. That corresponds to the limit where tau goes to 0. Because in that limit, the Lorentzian geometry, so we're talking about Euclidean geometries, but in the Lorentzian geometry, these defects would be moving on a time-like path, time-like junction condition. The Vadia collapse that we studied previously, it was a null junction, and so that was the limit where these are at 0 separation. And that was also studied by VJ and collaborator before we studied it in CFT. Last but not least, is the match to the wormholes. This is pretty easy now that we've got everything set up. So the simplest wormhole in this case is a wormhole that looks like this. Start with a solution. You start with a solution of Liouville, which has that was supposed to defect. I've been making those. There's one line defect and two vertex operators I and J. You start with this solution of Liouville, you put it into this dots that turns it into a three-dimensional geometry, and you get a wormhole that looks like this. And so this is the analog of the C0 wormhole. And so e to the minus the gravitational action. This wormhole is C0d of odd squared. That's calculating for you the variance of the ensemble. On the left and right of the in this case, yes, these defects are going across. So it's the same on the left and right. So in comparing to Liouville, the summary is that when you do Liouville with a ZZ boundary condition, you get single boundary solutions in the bowl. When you do Liouville without any ZZ boundary condition, then you get two boundary wormholes in the bowl. We can look at more complicated wormholes. I'm going to do this. I'll just draw a picture and say this in words since I'm out of time. But here's an example. So here's an example of a four boundary wormhole. And now you can send with these you send these shells across to the four boundaries. So this should be dual to the ensemble calculation of D dagger D to the four average. By the way, I should have emphasized that once you add angular momentum, these gravity calculations get pretty difficult. This in the previous approaches to this problem, like using in our original paper, we use this quasi-Fuchsian math that okay, and then in the more recent Virasor approach, to calculate these wormholes using topological field theory formalism, but actually in these wormholes gets pretty hard, especially when you have angular momentum, and especially in the situation where the moduli are different on the different boundaries. So I drew the picture as if it's fairly simple looking, but there's a bunch of moduli here. There's these distance between them, which can be different on the four boundaries. And then for each of those, there's also the relative shift in the transverse direction, which we used before to turn on angular momentum. Okay, so there's lots of moduli here. And constructing the wormholes like that for point particles is extremely hard. We didn't succeed in doing that for the more than two boundaries. In the original paper, you have to use Virasoro TQFT to do those calculations. Whereas here, you can do it much more explicitly. The way we do that is by chopping into pieces. Okay, so we could calculate the gravitational action of this directly just using the metric. The way that's done is by breaking the calculation into two steps. So first, we break this into 8 pieces. So I just drew one of them for you. So we get 8 of those. If you think about breaking it up into these wedges that go all the way around. So you chop into 2K. If for a K boundary wormhole, you chop it up into 2K pieces. And in another paper with Wanzhen Chua, we showed how you can calculate the action of these wedges. So the gravitational action of these wedges has contribution from the bulk term and the matter, and there's a contribution from corners at the boundary. But there's a nice formula for these things, which you can think of as a formula for a gravitational wave function along the lines of what people have done in JT gravity in 2 dimensions. So when people do these more complicated calculations in JT gravity, the way they do it is they take these complicated higher topologies and chop them up into a bunch of pieces, which have simple wave functions, and then glue them together. And it's only the final integral that's sort of non-trivial, because you've chopped it up into a bunch of Bessel functions. And then the final integral, well, maybe it's the Bessel functions, into simple ingredients. And this wave function calculations that we can do in this case is a difference is that we only know how to calculate these wave functions for spherically symmetric matter configurations above 2-dimensional gravity. But this is spherically symmetric, so we can use that whole technology and construct these wormholes in great detail. And the answer, of course, is that when you do the average, as I described at the beginning, that these calculations of the gravitational calculations of the on-shell action of the Gaussian average of these CFT correlations. When you chop it up in wave functions, really easy to see because you chop it up into these 8 pieces, and then you integrate over the energy and angular momentum in the center. That becomes the sum over internal states in the CFT calculation. So, long story short, calculate these gravitational actions, and they average over CFT data. So I'm just going to conclude with a couple of comments and then be done. So let's see. So the first comment is about ensemble averaging versus coarse graining. Okay, and we discussed this in the discussion session last week, but to sort of recap and apply it here, I think when you're studying a low energy theory, when you're studying a low energy effective theory, which is the point of view that we're taking here, there isn't a distinction really. They're both true. That you can either, all these calculations I described as ensemble averages, but you can also describe them as calculations of coarse-grained observables in a fixed theory. Okay, and there's a procedure for taking the wormholes that I've described here and turning them into coarse-grained observables in a fixed theory. The distinction, the sort of more subtle question of whether, is gravity an ensemble average or is it a fixed theory? That's really a question for the UV. And it's not one that you can answer using the low energy theory. Both are true. And how you embed it might depend on can depend on what you do at higher energy. Yeah. Um, well, you could call that part of the averaging, as opposed to coarse graining within the theories, right? So if if you start with a discrete spectrum and then you average it, you end up with a continuous spectrum. So I don't think I don't reason that you would need to coarse grain um, if you have an ensemble. Right. It's enough. Yeah. Yeah. It would smooth out the discrete data. Yeah. Well, that's like, well, what kind of observables? Um, I don't know of situations where those are leading, but any observable would be sensitive to it if asked very precise question. Like if you function squared in the usual ensemble duality, that's already sensitive to non it's just that it will show up as um, what appears to be a sub term. Now, is that is, are sub if you have moduli and what happens there, where you are in moduli space, something that was Gaussian at one point in moduli space might look like a non-Gaussianity at some other point in moduli space. So depending where you are in moduli space, is different terms that will dominate and appear to be Gaussian. The reason it can make sense is because something that's Gaussian in one channel can be non-Gaussian in a different OPE channel. The last comment, I'll just comment I was just going to make was about higher dimensions. I think for the kinds of things that I've described, it's mostly conceptually similar. As we sort of touched on in the questions and everything, the big difference in higher dimensions is that the notion of descendant needs to be replaced by the notion of low energy effective field theory. Now, we only want to do averaging or treat as random the black hole microstates that are invisible to the low energy field. Anything that would correspond to stress tensor exchange of some finite number of stress tensors or multi-stress tensors, or anything you can calculate in the low energy effective theory that's not a black hole should not be random. It's clearly, it's more like mean field theory, expansion of 1 over n. So the conceptual difference is just that you first need to sort of mod out by the low energy theory and treat everything else as random. It seems very hard to do that in practice, but I don't see any major conceptual thing. Okay, let me stop there. Okay, thanks. No, let's see, that's not the same formula. So Martin was studying states that Martin was studying a sort of they're sort of doing some of what they're doing is a finite temperatured version of what I've described here. So they're studying states that you get where you insert a dust shell in the middle, and then you cut. And they're studying these states in multiple copies of the theory. Um, I'm the formula for the variance is not the same formula, but I don't quite remember how it's related. Maybe G-Ben remembers if they have a. Is it? I don't think it's the same variance. Okay, yeah, I guess there are many different ways you can. There are different configurations, and I don't remember exactly how that's related. I don't think that can happen. They have to pierce. Well, I don't know how to, but there's no, they don't know which way they're oriented. That's up to gravity to tell them which way to orient. Um, you just have a 3-point function squared. Um, maybe there's a solution where it goes through the shell, but then I guess you'll again be in a situation where you have to understand how the particle interacts with the shell. No, it's not that I think they'll be self-avoiding. I think there very well could be solutions like that, but they probably depend on the detail. I don't think you'll be able to get them just from junction conditions. So then they're going to depend on the details of what the shell is actually made of. Yeah, in this case, I think, yeah. Yeah, I think they're there in principle, but probably non-universal. Right. You're saying there might be universal P? Is that, or, yeah, no, I agree. Yeah, yeah, that's true. I see. Yeah. Gravity could give you the scaling or something. Maybe the non-universality there is just some order one coefficient or something. But maybe it doesn't, maybe it's pretty universal. Yeah. What's next for the identity block? I don't know, but I would like to understand better in higher dimensions. I I treated it in the words that I said as being maybe sounding a little hopeless in higher dimensions. But now we have this thermal effective field theory, for example, and of of the Caltech group, and the so maybe maybe that's one direction to go, is higher dimensions. Um, the thermal effective field theory and the asymptotic OPE data that they have is not directly related because it's not into Einstein blocks. It's organized into conformal primaries. But maybe more can be done. As far as 3D gravity, I don't know. Maybe it's a question for the audience. What more can we what more can we say? Uh, you mean with shells, I guess, is it? Yeah, yeah. Yeah, I think that the general question, including line defects, line defects probably, if you thought about them much, they probably sound like sort of obscure, like why would sort of obscure. But it's something that's become more and more important for Bootstrap and more and more interesting because people have understood that there's lots of things you can access using line defects and interesting properties of defects in the Bootstrap that go beyond what you can get from local operators. And in many cases, line defects, like in this case, are actually simpler than studying local operators because line defects can incorporate more symmetries than local operators. So I think like trying to systematically include line defects in various other things we do in holography will also be an interesting way to go. I don't know if that's identity block, but yeah. Yeah, yeah. Well, conformal people are also studying conformal defects, line, well, defects and interfaces and boundaries. In this case, I think it is. Yeah. These are not conformal in the sense that like they float all in a conformal field theory. A defect will always flow to something conformal at large distances, but these do not preserve conformal symmetry on the defect. The ZZ boundary condition does, but the e to the m integral phi does not. So the defects that I was inserting are not conformal defects in the sense that the bootstrappers and the CFT people use the word conformal defect. They're defects in a CFT, but they don't preserve the conformal symmetry on the defect. Yeah, I think that would be like a conformal defect. So yeah, um, the boundary conditions in CFT are or interfaces in CFT are boundary conditions in the double theory. But if you want them to be conformal boundary conditions, then you get conformal interfaces. Yeah, yeah.